Good afternoon, everybody. It is a great honor to present our invited speaker today, Professor Malik Maza, which is a chair, UNESCO-UNISA ITL NRF Africa Chair in Nanoscience and Nanotechnology, joint staff of the University of South Africa. Professor Maza is a native of North Africa, as I understood, Algeria, holds a PhD from the University of Paris 6, is the current incumbent in South Africa of the UNESCO-UNISA-iThemba NRF Africa Chair in Nanoscience. He is a joint staff of the University of South Africa and the National Research Foundation of South Africa. He is a fellow of various academies, including the African Academy of Science, the European Academy of Arts and Science, as well as the National Academy of Science of India, the Islamic Academy of Science, and the Royal Society of Chemistry in London. Professor Maza has received several awards, among which the African Union Network Krumash Award for Excellence in Science and Technology, and the Galileo Galilei Award by the International Commission for Optics, ICO. Now, I would like to invite Professor Maza to start delivering his talk about nanofluid by pulse laser in liquid, emerging Coolants family. Please, Professor.
In fact, just recently, Google and the government of Finland have signed an agreement for a long-term to be able for the usage of the data centers waste heat recovery. As you are aware, data centers do consume an extensive amount of energy. Sometimes data centers do consume more energy than the national grid allows. That is the case in Nigeria, in other parts of the world. And India is not different from other parts of the world in this regard. And the idea is to use the heat generated by data centers to be able to be used and transformed as an energy supply for cities, and therefore to ensure that that heat is not lost. And for such, it is intended to use or to innovate or to come and engineer a new emerging coolants, a new type of heat transfer systems. And in that regard, nanofluids are a part of it. Next, please, Prof. Sankaran. Within this talk is given within the framework of the UNESCO-UNISA-iThemba Labs NRF Africa Chair in Nanosciences and Nanotechnology, as well as the Nanoscience African Network. Allow me please to mention that both of them have been, we have been assisted and we have been supported both morally and financially by, a role model to all of us. That is Professor Siana Rao from Gian Kasar, Bangalore. So the UNESCO chair is headquartered in Pretoria in South Africa, while the Nano AFNet is headquartered, administered in the Cape, in the Western Cape, still in South Africa. Next, please. The mission of the UNESCO chair and the Nano AFNet are geared towards human capital development and training postgrads at the level of MSc and PhD from all over the African continent and the South. And when it comes to the South, mainly 4 major countries do come out. That is China, that is India, and that is Pakistan and Iran at a certain extent. The outline of my talk, colleagues, junior and senior, is split in 4 major parts. I would give an overview about nanofluids, somehow a simple one. Then I would, define why nanofluids are extremely important, in particular in view of heat management and heat transfer, both in how can I say, in data centers, as well as in nuclear reactors, as well as in automotive industry. And you would see that one of the most competitive techniques which would allow to to engineer advanced nanofluids are lasers, or laser ablation in liquid solution. As you can see, colleagues, nanofluids are not new. In fact, the one who has came with the idea of a nanofluid is not more than James Maxwell, the father or the god of electromagnetism somehow. So you would understand that, how can I say, to have Maxwell involved in initiating and thinking about the nanofluids is of extreme importance, because he was the first one who set up the scene in terms of thinking about enhancing the thermoconductivity of a normal fluid, that is water, that is ethylene glycol, that is oil, but incorporating in them particles. In that time, they were not able to make nanoparticles, but rather to make large particles. But nonetheless, now it is possible to implement the idea and the vision of James Maxwell when it comes to nanofluids. And of course, because the era of the field of nanosciences and nanotechnology, that has allowed us to master the synthesis of and the control of the size as well as the shape of nanoparticles by different physical as well as chemical methods, that now the nanofluids idea or approach is a reality. And the Department of Energy, in effect, in the US was the major driving force in it. And in particular, Professor Choi from Argonne National Laboratory, who was mandated by the National Nanotechnology Initiative in the US in that time of President Clinton, to embark in a nanofluids national program in that regard. This, how can I say, as I was mentioning, in effect, I have just highlighted the major milestones in terms of dates when it comes to the development from a theoretical point of view and the experimental point of view, nanofluids. In terms of applications, you would understand, colleagues, that the major component is removal of or heat management in data centers, both cooling and removing that heat to be used furthermore transformed in form of electricity by CSP technology or by other method, steam, water, that kind of standard techniques. Nonetheless, the other major field of applications are any automotive or transportation system. Any transportation system using a normal thermodynamic based heat engine requires cooling, and that is how can I say, using nanofluids instead of standard fluids would allow to remove heat easily from automotive engines or transportation and vehicle engine. The same thing also for industrial cooling applications, and also some of potential applications in solar energy, both in the concentrated solar power and photovoltaics. As you are aware, a photovoltaic, for example, an increase of 1 degree in a photovoltaic silicon-based system decreases its efficiency by 5%. Any increase of temperature of 1 degree, I repeat myself, colleagues, to make it clear, any increase of 1% of a photovoltaic silicon-based will decrease its efficiency by 5%. Therefore, it is necessary to cool down photovoltaics and to keep them at a low temperature to ensure that the rate of conversion is high and is not affected. Therefore, there is a trade-off somehow. The same thing for when the Department of Energy in the US, the DOI, and the DARPA embarked in nanofluids. Initially, in effect, it was data centers, but also nuclear reactors. The idea is to cool nuclear reactors and ensure using not water, but using nanofluids, because water, once, how can I say, once the water, once the how can I say, the reactor is under thermal duress, the water creates bubbles at the level of the walls, and in particular at the level of the interface between the coolant and the reactor. And these bubbles do how can I say, play a role in minimizing the heat transfer, and therefore it is necessary to use nanofluids to ensure that the critical heat flux is conserved optimal at a certain extent. And of course, space industry is interested to cool the nanoelectronic in this embarked satellites, or in satellites in general. Next, please. Well, colleagues, here is more or less the Enquist graph. The Enquist graph reports simply said different technologies relatively to their CO2 footprint. And as you can see, colleagues, as you can see, the technologies which possess a CO2 footprint in terms of cost abatement positive are technologies which would generate extensive amount of CO2. Those technologies which have a negative cost of abatement in terms of CO2 are technologies which would at the end produce a minimum or a minute amount of CO2 footprint. And you would see, colleagues, I singled out in a red, in a pink here, fuel efficient vehicles, water heating, as well as fuel efficient commercial vehicle, and so on. We should remember, colleagues, that the transportation is the major CO2 emitter at certain extent, and not the coal stations, but the transportation itself. And therefore, having involving a technology which would minimize the production of CO2 footprint in automotive, for example, would be ideal. Next, please. And here I would like really to take some time of your time, colleagues, just to set the scene, to be sure that you will be convinced that this hot topic should be more or less colleagues from India should be involved in it. Simply said, colleagues, this is an engine, a standard engine of a car. Up to now, we use, when the pistons are operating, they do generate heat, because the thermodynamic cycle of Boe-Rochas is not as effective. So when the piston operates, they do generate heat, and that heat is lost. And we need to remove that heat from the piston area. Therefore, we use water which goes through the radiator, and it comes at the level of the piston. It removes the heat, and the water is heated and comes back to the radiator with a fan and so on, and it goes for another cycle. Unfortunately, colleagues, unfortunately, the ideal coolant that we are using is water, but the water, the thermoconductivity of water is less than less than 1 watt per meter per Kelvin. So the idea is to, how can I say, use a nanofluid which has a higher thermoconductivity. If so, if it has a higher thermoconductivity, that means for each cycle, the nanofluid will remove a higher amount of heat from the engine and comes back again to the radiator, lose that heat easily because its thermoconductivity is higher, and it goes for a second cycle, a third cycle, a fourth cycle, and so on. So the usage of a nanofluid will allow to, at each cycle, to remove a maximum of heat from the engine, and therefore to make the engine working under less thermal duress at a certain extent. And therefore, if it is under less thermal duress, that means that it will consume, the lifetime of the engine will be higher, one, and second, that the amount of fuel consumed at each cycle is less, and therefore economy of fuel consumption. And the third is less fuel consumed, less NOx emitted, less CO2 emitted, and therefore the, how can I say, the automotive industry is extremely, very, very highly interested by this new emerging type of coolant, which are nanofluids. Next, please, Prof. And just to get to set the scene, colleagues, as you can see here is the thermoconductivity of different materials, organic materials, as you can see in the first portion. In the second portion, the standard heat transfer fluids, that is water, ethylene glycol, and mineral oil, used in a number, in the bulk of the engines. And there is a part of metals and their metal oxides. As you can see, colleagues, the metals and their oxides, the thermoconductivity is at least 2 order or 3 order of magnitude than that of the standard heat transfer fluids, which are water, ethylene glycol, and mineral oil. And thermodynamics speaks, how can I say, if we could use metallic nanoparticles or their oxides in suspension in a normal heat transfer fluid, certainly the thermoconductivity will increase, because the thermoconductivity is an additive thermodynamic component. So that is why now the move is to go for nanofluids. Unlikely before, fellows who have tried to use micrometric type suspension of particles. Unfortunately, micron size particles would not make it, because under gravitation they will settle down, and once they settle down, we will lose the notion of nanofluid. But if we use instead the nanoparticles under Brownian motion would definitely, how can I say, overcome the gravitational effect, and therefore will stay in suspension. And therefore, the thermoconductivity of a nanofluid consisting of a standard fluid within it nanoparticles would definitely have a higher thermoconductivity. Next, please. As I mentioned, colleagues, a nanofluid consists of a suspension of nanoparticles, nanoscaled particles within a standard host fluid. That is oil, that is, how can I say, mineral or water or ethylene glycol or any other oil. And because the nanoparticles are small, nanoscaled, therefore the Brownian motion component will definitely overcome the gravitation, and therefore you will have always a suspension. And therefore the thermoconductivity, as you could guess, colleagues, the thermoconductivity will be given by the thermoconductivity of the fluid itself plus the thermoconductivity of the nanoparticles, at least in terms of the static component. And of course, colleagues, you would understand that the real one is the thermoconductivity of the host fluid plus the thermoconductivity of the nanoparticles plus a Brownian motion component due to the motion of the nanoparticles. Next, Prof. Again, colleagues, James Maxwell in 1867 came with an approximation somehow of the thermoconductivity of a composite, and he derived it in the second block, whereby the K static, as I mentioned, colleagues, the effective thermoconductivity of a nanofluid is given by the static component plus the Brownian motion component. For the moment, we just go for the K static one. At least the K static one has been derived by James Maxwell. It's in a simple way. It's given by equation number 2, and you would expect that that component due to the nanoparticles would definitely would depend on their volumic concentration, as well as their diameter, and so on and so on. Next, please. Since the derivation of James Maxwell in terms of the thermoconductivity, the effective one of a nanofluid, a number of theoreticians embarked in more or less deriving it, taking into consideration a surface layer surrounding the nanoparticles with the fluid, and other approximations and other considerations, the shape, as well as the size distribution, and so on. And quite a number has been done in that regard, in that sense, indeed. And all of them, they show clearly that the effective thermoconductivity of a nanofluid is higher than the host fluid, and higher at certain extent to the standard values that we use for standard coolant. Next, please. Those who managed to show experimentally the effectiveness and who registered high thermoconductivity, by far higher than the water and the ethylene glycol and mineral oil and other organic materials, was Choi and Eastman at the Department of Energy in the US, Masuda in Japan, Shinpyo Lee in Korea, and Wagner in Germany. Next, please. These are from experimental point of view. Now we come for the synthesis. Different techniques have been used, but the best one, the one who gave the best results somehow, is the laser ablation in liquid solution that we call also PLAL or LLSI. As you are, I think, colleagues, all aware, what is a PLAL? It consists of having a target covered with the host fluid that we would like to, within which we would like to have our nanoparticles, and we come with the laser and we ablate that material, that target, rotating target, to ensure that we are not ablating at the same position, but rather to, how can I say, rotate it to get a better type of size distribution, and how can I say, and that the absorption coefficient will be somehow homogeneous within the target itself. And the advantage of this technique, colleagues, you are familiar certainly with it in a way or another. The advantage of this technique is it is a one step straight to make nanoparticles and nanofluids. One. Second is that the ablation, the nanoparticles are produced in the host fluid itself and not in another fluid. Third is that generally speaking, at a low concentration, there is no need for a deflocculant, because the host fluid molecules act as due to their molecular dipole, act like a deflocculant somehow, and allow the nanoparticles not to coagulate somehow. So this technique is really, how can I say, has gained credential all over the world, and all those who are involved in the synthesis of nanofluid, they do prefer this technique somehow. Of course, the nature of the laser radiation depends on the absorption coefficient of the target and the transmission of the fluid to that wavelength. Next, please. Well, colleagues, you are very well aware about the different phenomena that are taking place. There is, of course, absorption of the photonic absorption, ablation, in cavitation, and acoustic transient, and so on. What is sure, colleague, is that the science of it is not as established yet. Yet, indeed, quite a lot has been done on ablation on materials with the liquid, with the surface liquid layers and so on. But still, there is quite a lot to be done in this regard. What is sure is that cavitation bubbles play a major role in this, as well as the plume plasma expansion in relation to the thermoelastic expansion and so on. So I don't want to go through the details, but generally speaking, the ideal, laser is a neodymium, or if we are looking for very small nanoparticles, that is a femtosecond type lasers and so on. Well, here, colleagues, I would like just to share with you some typical examples which have within which we have obtained the highest, absolutely the highest enhancement of thermoconductivity so far. I singled out just one or two examples. In this example, colleagues, we have fabricated graphene carpets, graphene nanosheets grafted with the silver nanoparticles. You can see them as if we have graphene carpets on which we have grafted nanoparticles of silver. Why graphene? Graphene because it has the highest thermoconductivity so far. It's better than that of diamond. Second, silver, we took the silver because the silver has the highest thermoconductivity of metals, and not the copper by, say, or aluminium, but the silver. So by conjugating these two materials which have a high thermoconductivity, we were expecting to obtain a nanofluid. Of course, both of them have been ablated in a normal standard coolant fluid, that is, for example, here the ethylene glycol, which is used extensively. It is that liquid, either pink or blue or green, depends on the country where you are, that you use in your car engine. So here in this case, we have made we synthesized this by laser ablation. First of all, ablating graphene in ethylene glycol, making a nanoplatelet and nanosheets of graphene in ethylene glycol, then changing, immersing the target of silver in it, and trying to have, how can I say, to irradiate, to ablate silver nanoparticles, which of course, because silver is polar, and therefore it would definitely come and graft, at least by van der Waals forces, on the surface. Maybe not physical, not a chemical absorption, but at least a physical absorption. Next, please, Prof. Here, a typical case of graphene on the left side, colleagues, on graphene sheets. As you can see, they are thin. It's not a single sheet of graphene, but rather a superposition of sheets of graphene. But nonetheless, it's a carpet of graphene. And on the right side, we have nanoparticles of silver nanoparticles. Next, please. And here, colleagues, as you can see, before we have, of course, we have had to use Raman to identify the 2D and the 2G signature of the graphene sheets. And here we have silver nanoparticles on the graphene sheets. And how can I say, also within this, it is possible to identify that we have indeed silver nanoparticles on graphene, because the enhanced Raman signature due to the silver nanoparticles, because how can I say, even if the 2D and the 2G of graphene can be easily observed, but due to the local field between two nanoparticles of silver, the field is enhanced to, how can I say, with a factor to form factor at the level of 10 to 12, 10 to 7 to 10 to 12. So it is possible to identify that indeed it is silver nanoparticles decorated on a graphene. Next, please. Then we have to go for thermoconductivity measurements, colleagues. And here we go for the basic one. It takes time, certainly, yes. It takes, it's time consuming relatively to laser-based approaches. For example, like the one of thermal, transient thermo reflectance and so on, where it takes some seconds and even less. And here it takes hours. But nonetheless, when we use the hot wire, the platinum hot wire based technique, we are capable to measure the thermoconductivity of the nanofluid, as well at different concentrations, as well also we compare it to the host fluid itself. Next, please, Prof. Here, colleagues, is the thermoconductivity for different systems. The first one at the bottom here, the thermoconductivity from around 20 degrees Celsius around to up to 50 or 45 degrees Celsius. This is unfortunately the limitation of the hot wire, because how can I say, out of this range there is a huge amount of fluctuations. So just to be safe, so that we represent only the thermoconductivity within this range. For the first curve of the bottom open circles, it's the silver. It is the thermoconductivity of ethylene, pure ethylene glycol. So you can see it's around 0.32, 7 watt per meter per Kelvin. And when we take graphene nanosheets, very low concentration in ethylene glycol, it is the second curve, colleagues. It's the square, open square, So it moves from 0.327 to 0.347, something like that. Maybe, colleagues, for us, it is not high, but it is high in terms of thermoconductivity. It is a good enhancement. It's around 625%. Now, if one take silver nanoparticles at a higher concentration, optimizing concentration, yet they will not coagulate. It's the third curve, and that is the pink squared. The thermal conductivity enhancement is around 12.5%. Now, if we take the silver nanoparticles grafted on the graphene, colleagues, the thermal conductivity is given by the top curve, pink circles, and that is, as you can see, relatively to the bottom curve, which is pure host ethylene glycol, the standard one. The increase is around 33%, and this is not negligible when it comes to thermoconductivity. It is high. It is high. An enhancement of 33% is just very high. Next, please, Prof. And as you can see, colleagues, relatively to all the thermoconductivity nanofluids have been synthesized worldwide. As you can see, colleagues, here 33% is the largest so far registered worldwide on a nanofluid somehow. And it is considered as a reference with the Department of Energy, in particular at Argonne National Laboratory, now as well as with the nanofluid team in in Germany by Chrysler in particular. Thank you. Next, please, Prof. Colleagues, you would agree with me that in effect the hot wire approach is not effective. The one which is very effective are laser based. The transient thermoreflectance in effect are far better because they would require relatively to colleagues relatively to the hot wire and the classical ones where the size must be bulky. Laser-based optical methods, laser-based are far better. Why? Because they would require a minute amount of material, one, and that the measurements time is not in, how can I say, it can be in milliseconds and microseconds even, and even faster. So how can I say, we are by how can I say, giving this talk to a photonic community, a respected photonic community as yours, we are thinking about kind of exploring possibilities of cooperation, in particular with Prof. Umberto at the ICTP in Trieste, and of course Prof. Sankaran, in exploring the usage of transient thermoreflectance to measure the thermal conductivity of nanofluids in, how can I say, in a more advanced way. Next, please, Prof. I was mentioning, colleagues, that if you do remember at the beginning, in the derivation of the thermoconductivity of a nanofluid, the effective one is equal to the K static plus the K Brownian component. And the K static is given by somehow the thermoconductivity of the host fluid itself and the thermoconductivity of the nanoparticles within a certain approach, and that is, how can I say, and the approach of James Maxwell is just perfect. It describes very well, how can I say, that model is enough. But as you can see, colleagues, here, for example, if we take thermoconductivity of silver nanoparticles in ethylene glycol, colleagues, what happens is that, as you can see, colleagues, within the temperature around 20 to 50, at different doses, fluences, the thermoconductivity of the nanoparticles have a tendency to increase above 40 degrees Celsius, have a tendency to increase faster than at low temperature. This was considered due, and this is for all the different doses, except the highest dose, the highest fluence. What is sure, colleagues, is that this is likely to be due to the thermal conductivity due to the Brownian motion. Next, Prof. So, as I mentioned, colleagues, the idea is to show that indeed the thermal conductivity, the Brownian motion, is related to increase of temperature, and therefore a statistical consideration whereby you consider that you have two particles or one particle moving from a hot zone to a cold zone. What is the heat transfer from the hot zone, hot region to the cold region? And we go, how can I say, calculate the heat exchanged, transferred by nanoparticles within, how can I say, through a certain cross section with a velocity, average velocity v, and how can I say, calculating the velocity v, it is possible, and quantifying more or less the Q net, the total net heat by the n particles within that volume v transferred from the hot zone to the cold zone. It is possible to find that in effect the Brownian motion is proportional to the square root of the temperature. Next, please, Prof. And indeed, you'll, how can I say, by playing on the equations and so on, it is possible to find that the Brownian motion is proportional to the square root of the temperature, and inversely proportional to the the size of the nanoparticles, and therefore the quite relatively rapid increase at above 40 degrees Celsius. That is due to the Brownian motion, and it shows clearly that how can I say, at a lower concentration somehow the Brownian motion can play a major role. Next, please, Prof. And again, colleagues, I would like just to reiterate, it's an invitation to all of you who are who could assist us in using laser-based approaches to measure the thermoconductivity of nanofluids. We are really open for it, and we will be, how can I say, as we have discussed with Prof. Umberto in ICTP and Prof. Sankaran, hopefully we will be able to, how can I say, create a network in this regard relatively to the nanofluid. Thank again, colleagues. The big picture here for the nanofluids is the, how can I say, to try to minimize the CO2 footprint of the automotive or the transport sector, being it large, small vehicles, being it aeroplanes, being it boats, whatever. Wherever there is a possibility to remove a heat from an engine and to make that engine operating under less duress, therefore a long lifetime cycle, one, and minimum of minimum of fuel consumption, and therefore a minimum of emission of NOx and CO2, that would be ideal. And the transportation sector is extremely critical in that regard, and it's a demanding sector for this new family coolant of nanofluids. Next, please, Prof. A reality now which is taking place is the usage of nanofluid in concentrated solar power, whereby instead to use just a normal liquid and normal oil or water within the CSP, now nanofluids are used to ensure that the maximum of heat is transferred from the absorption of the top selective solar absorber to inside the tube, inside the copper or the stainless steel, to the colporteur fluid. Again, I think, colleagues, I was just to mention that it will be unwise and unfortunate from myself to express my gratitude to all the fellows who contributed to this work, and they are from different parts of the African continent and the South, Iran, India, Pakistan, and Bangladesh, as well as Oman from theoretical point of view. Next, please, Prof. And I wish just to express a special thanks to all our female students who are working in this field here, who allowed us more or less to optimize and advance extensively in the field of clean energy and minimizing the CO2 production by this type of technologies, and contributing to the sustainable development goals, being it gender equity and clean technologies. Next, please. And by that, colleagues, Dhanya Vad, I thank you for taking off your time listening to my presentation, and I hope that we will be synergizing to and gain from your expertise and share our know-how together in this field of nanofluids by laser ablation in liquid solution. Thank you. To you, Chair.
Thank you, Dr. Maza, for the very nice and interesting presentation. Now we are open for question. Everybody can open the phone and give directly the question, but allow me to give you the first question. I didn't see in your method, in your comparison there, gold nanoparticles and carbon nanotubes when you compare. Can you explain and give you more details?
Thank you, Dr. Prof. Umberto. Indeed, gold and carbon nanotubes are ideal. But how can I say, we have made, relatively to carbon nanotubes, graphene has a higher thermoconductivity than carbon nanotubes, but nonetheless, and the usage of silver is based on, how can I say, in terms of cost effectiveness. We, how can I say, we prefer using silver than gold because it's cost effective. But nonetheless, yes, indeed, quite a number of work have been done with carbon nanotubes and gold. And the ideal is to, how can I say, to use rather copper and aluminium than gold or silver.
Thank you. I think that I know that Professor Sankarama did some work, even we have something together in nanofluid, and that thermal length is very effective for that goal. I hope we can do together something. If there are more questions, please go ahead directly.
Yeah, yes, I have a question. Prof. Maza, this is Joe Sargent from Malaysia. And I think we have collaborative publications using through this Prof. Fabian Izema from University of Nigeria.
Yes.
Yeah. Good to see you here. I had been in many conferences where we were co-speaking, but we couldn't get a chance to interact. Good to see you here. Good to see you here. I have some general questions like how stable this suspension is, especially when this inorganics like gold nanoparticles or copper oxide or any of those kind of inorganic nanoparticles, when they get into this organic medium like ethylene glycol, how stable those suspension is, and is there a critical concentration that you can suggest to be for this nanofluid to be stable?
Yes, you are absolutely right. You really touched on the hot point and the most, how can I say, the most critical aspect of nanofluid. First of all, the theory shows us clearly that we should not go above 10% volume. Above 10% volume, the thermoconductivity of the composite decreases. So there is no need to go above that right. Critical threshold. That's one. Second, even if we go to low concentrations, how can I say, the stability is of a concern.
Yeah.
So generally speaking, as you have you pointed out directly, that the electric dipole of the bulk of the heat transfer media is not high, and therefore we could expect that how can I say, we'll be obliged to put a deflocculant, a molecule which would anchor on the nanoparticles to ensure that they will not coalesce.
Okay.
But how can I say, what is sure is that higher is the, as much as we are below 10% volume, as much as the concentration is not high, the nanofluid is stable for some weeks, some months maximum.
Okay.
So it is necessary to use a deflocculant. But now, when you use the deflocculant, you would affect the phonon contribution of the surface layer, and therefore, how can I say, you would lose somehow in terms of thermoconductivity from the fluid to the nanoparticle itself. So there is a trade-off somehow. There is a trade-off, and there where the shape effect comes in, and directly what Prof. Umberto was mentioning, the carbon nanotubes or the graphene, instead just spherical nanoparticles. But there is a trade-off here. It's a really, truly an optimization. It's an engineering optimization so far.
All right. Okay. Thank you.
Thanks a lot.
Sir, you mentioned about graphene nanofluids, then laser ablation using graphene as the target. So what will be when graphene is used as the target and ablated, what will be the state? Will it be in the graphene form? Will it remain as a 2D, or it will break into carbon atoms or chains? One dimensional, will it to one dimension?
Yes. Yes. Professor Karaman, you are right indeed. Here again, it's an optimization. We always, everybody takes a graphite target. And when we have the right wavelength, the right coefficient of absorption, at the right fluence and so on, we have graphene sheets. We don't have a single sheets, but we have a set of graphene with a set number of sheets. And graphene are stable somehow.
So you are using graphite as the target and ablating it.
Correct. Correct.
Sir, can you talk about the recently another class of fluid, ion nanofluids, using the base fluid as ionic fluids as the base? So since 2010, another class of material, that is ion nanofluid, also is emerging. Can you comment something on that?
I must say, how can I say, the usage of ionic fluids is of an interest indeed. You are absolutely right. Except that quite a number of ionic fluids are not are affected during the laser ablation, and as much as the literature which came out, which is limited in effect, it's not much. I must say I have not read so much in this perspective, so I really beg your pardon. I just cannot help in, but definitely we would be interested to embark in this direction.
Okay, sir.
Thank you.
More questions? If not, Professor Sankaraman, I'll see you will.
So there are questions in the chat box.
Sir, there is one question in the chat box. Shall I read it?
Yes.
Yes. Sir, you are using graphene. Which method you are using for preparing graphene? This is question.
So what we do is that we prepare the graphene the same in one step. It's like, how can I say, for the silver nanoparticles, we take the bottom graphite target, high purity graphite target, and we ablate using, how can I say, using neodymium YAG. I think the neodymium YAG, if I do remember, there is, I think the right technical details, you can find them in one of our Nature scientific reports. I can send the list to Prof. Umberto and Prof. Sankaraman, and you can, how can I say, they can share that with you. What is sure is that we do use, we don't use the fundamental for the graphene. We take the high purity graphite target that we will immerse in the ethylene glycol and rotating it and ablating. And then once we have done this, we remove the graphene target and we put the silver instead of nanoparticle target, and we ablate. The details, I think, if you go to Google Maza and Nature Scientific Report, you will have found these ones, the ones that with the graphene with the silver as well as the gold as Prof. Umberto has pointed out somehow.
Okay, thank you, sir.
Dr. Mohammed, so actually, if we use this kind of technique, can we, how will we be sure about its reproducibility of these kind of systems, like the components of the systems?
Thank you so much for the question of reproducibility. In effect, it is quite reproducible, yes. And how can I say, we do never run one experiment. It's just a number of experiments to ensure the reproducibility, and up to now it is reproducible. And I do firmly believe that optical technique, laser-based techniques of thermoreflectance, transient laser-based, would allow us to do this faster than relatively to the hot wire. But what is sure, it is reproducible, yes.
So like, if you are looking for like industrial production, so these kind of techniques, can we scale it up using some flow reactor kind of things? You do have kind of design.
Yes, you are right. In effect, how can I say, as how can I say, a group in Germany who does produce these nanoparticles in a bulk, in liters, 10 liters per day. So it is possible to mass scale this approach.
Sir, one more question. Actually, like in laboratory conditions, these things are okay, but in the industrial scenario, suppose it's like a kind of high compression flow systems, how it would be like, for example, like silver decorated in graphene. So during this kind of high pressure reactions, whether you observe any kind of chemical change to the system, like oxidization of these kind of interfaces and these kind of issues, whether you are focusing on that.
Correct. Well, when you do when you prepare these particles in water, for example, you would expect at a certain moment you would have an oxidation of the surface. But well, here, as Prof. Umberto has mentioned, the gold and platinum are rather chemically inert. So how can I say, generally speaking, they do not oxidize. Silver does oxidize indeed, but not much. If it is in water, yes, but in ethylene glycol or mineral oil and so on, the oxidation is really rare. But what is that is not the case when you go for copper or aluminium, whereby you clearly see that the plasmon peak of the copper or aluminium does indeed shift spectrally. Therefore, there is a formation of an oxide layer at the top of it, and it makes that plasmon absorbance shifting extensively. But it is not the case for gold or platinum or silver.
Thank you, Professor. Thank you.
Thank you.
Dr. Malik, I was observing the electron micrographs of the silver nanoparticles. These particles are not having good monodispersity. So I think if you will be synthesizing these materials simply using the reducing agents, so even you can also cap with the ethylene glycol. So if these particles will be having more monodispersity, I think the system will be having more efficiency. As you are quoting here that in case of the silver nanoparticles which are decorated on the graphenes and in the presence of the ethylene glycol, 33% you have reported the value. But I think it can be augmented if we will be having the monodispersity in the particles, silver particles. Because in the laser ablation, we are not getting too much good monodispersity in the particle size. So,
Correct.
Can you comment on this?
Correct.
Yeah.
Yes, you are absolutely correct indeed. How can I say, the chemical methods are ideal for the monodispacity of the nanoparticles, of course, but it will be a two-step process. And how can I say, those who are interested by applications are they are more geared towards one single process or single step approach. Nonetheless, it looks like that when you go to femtosecond lasers, when you go for ablation with the femtosecond lasers, here the polydispacity is less and the monodispacity is of a higher quality. So it's in effect there is a trade-off somehow. But what is sure is the femtosecond regime allows to have a better degree of dispacity in terms of size.
Okay. Right, sir. Okay.
Thank you.
I think there is one more question in the chat box. CO2 decorated with copper.
I think he has asked that question, sir.
No, yeah, just place this in exact comment. Because some of the groups are now developing cerium oxide-based systems because they are more stable, but that is not contextually different. They are doing hydrothermal and they will mix it. It's a multi-step process. But the professor presented here is like how we can do it in a kind of single step. So I just put it as a comment in the chat line. Thank you.
Correct, colleague. How can I say? Now the tendency is to go for copper-based nanofluids. And how can I say? And the copper has a, how can I say? It's cost-effective relatively to gold and silver and other materials. One, and second is that how can I say? The copper oxidizes, always oxidizes somehow, and you have an interface layer. You have a core shell configuration of copper and a copper oxide surrounding it, and then interfacing with the nanofluid. And it looks like as if this oxide layer is in effect has a positive impact on the thermoconductivity because it induces a phonon matching type of bridge. It is still in discussion within the literature, but it looks like it is. But the copper is the one that everybody is moving towards it.
Okay, sir. Better.
Can I go ahead with the vote signs?
Yeah.
Good evening, all. We have reached the end of today's webinar session. I deem it a great honor and privilege to propose a vote of thanks for this great event organized by the Rama International Optronic Society Rios. On behalf of the Rios and the entire organizing team of ROS 2022, I extend a very hearty vote of thanks to our speaker, Professor Malik Maza, UNESCO-UNISA-iThemba Lab, University of South Africa, for gracing your important work and sharing with us your thinking and opinion toward your talk, Nanofluid by Pulse Laser in Liquid Emerging Coolants family. I must mention our deep sense of appreciation for you, sir, for giving excellent coverage to the topic related to nanofluid and thermal conductivity measuring. A special thanks to the chairperson, vice-chairperson, secretaries, and advisory committee members for their encouragement, support, and coordination to make this webinar successful. Our sincere gratitude and thanks to all the eminent personalities and other professors, faculties, and students from India and abroad for their active participation. Thank you all for making today's event successful with your contribution. All the participants are requested to submit their feedback for today itself before 10 p.m. Indian time. The link to the feedback form is available in the chat box. Our next webinar will be on Tuesday, 10th of November 22 at 7 p.m. Indian time on the topic Microwave Spectroscopy and Molecular Structure by Professor Rajapan Nair, Institute of Physical Chemistry and Electrochemistry, Leipzig University, Hanover, Germany. Once again, we thank you all for being with us, and we hope to look forward to your involvement in the upcoming webinars to make this series a tremendous success. Have a good day.
Thank you, colleagues. Thank you.
Thank you.
Thank you.
Good night.
Bye.
Thank you, sir.